In this chapter, we are going to take a look at simple gas laws. Please read the OER textbook chapter 9.2 for more detail of this chapter section and start your homework as soon as possible. Okay, so the simple gas law describes the relationship between pressure, volume, temperature, and number of mole of gas. Okay, so here are the simple gas law that we are going to visit today. Okay, so Boyle's law states the relationship between pressure and volume. Charles' law states the relationship between temperature and volume. Avogadro's law describes the relationship between mole and volume. And the last one is Amantan's law, which is going to describe the relationship between pressure and temperature. I don't care much about whether you will be able to memorize the sentence or not, but what I want you to take away from this lecture video is I would like you to understand the relationships between each of these. Okay, so you don't need to know what scientist is state what. What I want you to carry away from this lecture video is you need to understand the relationship between pressure, volume, temperature, and number of mole of gas. Okay, so that's my expectation. So now let's take a look at the first relationship, which is pressure and volume. Okay, so in this case, before we discuss this relationship, I would like to actually watch the lecture demo real quick, and we are going to establish the relationship between pressure and volume together. Okay, so in this syringe, we have a balloon in here. Okay, so this balloon has a certain amount of gas in it. Okay, so I already tied it. Okay, so what I'm going to do is that I'm going to close this end of the syringe. Okay, and then I'm gonna push the piston toward the balloon. So when I'm doing this, I'm actually increase the pressure inside the syringe. And we are going to see that what happened if the pressure inside the syringe increase, what happened to the volume of the balloon. Okay, so we're gonna take a look at that. Okay, so let's make an observation right here. And also at this temperature, I'm not changing any temperature as well. So temperature stay constant also. Okay, so the same as number of mole of gas. Okay, so I'm gonna push the piston toward the balloon. Okay, so as you can tell, right? So as the pressure increase, the size of the balloon start to shrink. Okay, so now if I decrease that pressure, you will see that the volume of balloon start to get bigger and bigger again. Okay, so I'm gonna. All right, from the lecture demo, you will see that the size and the pressure would be the opposite, right? So as you see, as the pressure increase, as the pressure inside the syringe increase, you will see that the balloon size, the volume of the balloon is actually decreased, right? The size of the balloon decreased. And vice versa, as the pressure decreased, you will see that the balloon is actually expand, right? So is the volume in the balloon is actually getting bigger, so the volume increase. Therefore, the relationship between pressure and volume of gas stated by Boyle's law would be pressure and volume are inversely related to each other. Okay, so they are inversely proportional to each other. Okay, so in this case, there are two things that I would like to emphasize. So the first one is the amount of gas in the balloon. Since I did not change any amount of gas at all, the balloon is still tight, very tight, right? So I tie it. So therefore, in this case, it's going to stay the same. Okay, so the amount of gas inside the balloon will stay the same throughout the whole demo. Whether I increase or decrease pressure, the amount of balloons still stay the same. Okay. The second one I would like you to jot down is the temperature. I also did not change any temperature at all. So therefore, in this case, temperature also stay the same as well. Therefore, pretty much what I can tell here, the conclusion of Boyle's law is that as the amount of gas stay the same, temperature stay the same. As you increase pressure, volume will decrease, vice versa. Okay, so that is the relationship between pressure and volume according to Boyle's law. And the real life example of this is going to be, for example, exhalation and inhalation, right? So for example, as you exhale, right? So the rib cage would contract, right? And also the diaphragm also moving up as well, causing the pressure going to be high, right? It's going to shrink the lung, right? So the volume of lung would decrease, right? So, and then as you, inhale, right, it's going to be the opposite effect, right? So the pressure inside that would decrease, and also you will see that the volume can expand as well. This pressure volume relationship can be used in scuba diving as well. For example, if you are way below the water surface here, right? So in this depth right here, you are going to experience a high pressure, and this high pressure is going to cause the lung to shrink. So therefore, if you are going to take a scuba diving course, is going to recommend, like when you are take the course, it will tell you to actually, when you are rise to the water surface, you have to do it in a small increment, so that way your lung will not like burst out and like causing you to die or whatever. So in this case, as you rise up to a surface of water, your lung is going to expand more and more as well. So in this case, again, as you experience less pressure, the lung would expand to a normal, what do you call, like condition, right? So same thing with this example as well. If you have a balloon at like surface level, like let's say like at sea level, is going to be a certain size. But if you let it go to like an upper atmosphere, okay, so you are going to experience that, because upper atmosphere has lower pressure than the pressure inside the balloon. You are going to observe that the balloon will expand, or the volume will getting bigger. Okay, so these are the real life example. So pretty much, again, the graphical representation for this pressure volume relationship, if we are going to describe this in graphical representation, you are going to see, if you plot between pressure and volume, you are going to see that these are going to be the relationship between them. They are inversely proportional to each other. Okay, so if you plot between 1 over pressure per volume, you are going to get the direct relationship here. Okay, so therefore in this case, if you are going to write mathematical equation to express the relationship, you will see that the volume and pressure are going to be on the opposite side, right? So indicate that they are inversely proportional to each other. So in this case, R is going to be the constant. And as I mentioned before, things that stay constant or stay the same in this case would be, temperature and number of mole of gas. Okay, so N is number of mole of gas. Okay, so let me actually write that down real quick. So this R, which is constant, is going to be the temperature and number of mole of gas. Okay, so N is mole of gas. Okay, if I rearrange equation, we're gonna get PV equal R, okay, which is the constant, right? So constant is gonna stay the same. Okay, so therefore, if you have a different condition, you are going to be able to have them equal to each other through that constant. So that's why in this case, P1 V1 equal to P2 V2 are expressed the two state or two set of condition between the pressure and volume that are different. Okay, so when are you going to use P1 V1 equal to P2 V2? This is when you are given two different set of condition. Okay, so jot that down. Okay, so this is whenever that you are see two different set of condition, you are going to use P1 V1 equal to P2 V2. Okay, so in this case, the temperature and number of mole of gas stay constant. Now let's take a look at example 1 here. Okay, so a snorkeler take a syringe filled with 60 milliliter of air from the surface where the pressure is 1 atm at an unknown depth. The volume of the air in the syringe at this depth is 7.5 milliliter. What is the pressure at this depth? Assume constant temperature, right? So in this case, again, it's telling you that the temperature will not change. So we see that it's given one volume, 1P, and then second volume. Again, we have two volumes. So I know that this problem giving me two set of conditions. So therefore, because giving me two set of conditions that involve with pressure and volume, I'm going to use Boyle's law equation, which is P1 V1 equal to P2 V2. Okay, so we should know that as the volume decrease, right? So it's going from 16 milliliter to 7.5. We should expect pressure to increase, right? So that means your answer come out should be greater than 1 atm. Okay, so that's how I check my answer. So all you need to do is plug in P1 V1 equal to P2 V2. Rearrange this equation, right? So for P2, you are obtaining 2.1 atm as a final answer. And again, this problem given 2 sig fig, therefore your final answer would have 2 sig fig as well. Okay, so don't forget the correct unit as well. Okay, now let's take a look at problem 2. I would like you to pause the video real quick and then complete this your own, and then check your answer with me once you finish. All right, let's take a look at your work together. So in this case, a diver with a lung capacity of 5 liters at the surface of the ocean descends to a depth of 20 meters, increasing pressure to 3 atm. What is the lung capacity in liter of the diver at 20 meters depth? Okay, so again, assume constant temperature and number of mole gas. Okay, so it's giving V1, it's giving P, right? So P2, right, is increasing to this pressure, asking you V2. Wait a second, it's give us 2 set of information, right? So one set is the first volume and the second set of the volume is what it's asking. But is the 20 meter is our pressure? The answer is no. Meter is not the unit of the pressure. So in this case, how do I know the pressure then, since we are missing, right? So what is the pressure V1? We already have V1. What is the P1? So remember, it's giving you the hint that is at the surface of the ocean. Remember, the atmospheric pressure at sea level or at the surface of the ocean is equal to 1 atm, right, or 760 millimeter mercury, right? So or 1 atm in this case. So that means you need to know that. Okay, so this is something that you need to know. So therefore, in this case, you are welcome to just use P1 V1 equal to P2 V2 because there are 2 set of conditions. Okay, so if you plug that in this case, you are going to get V2 equal to 1.7 milliliter. Does it make sense? Okay, so you need to check your answer as well. Again, as the pressure increase, the volume should decrease, right? So as you going from a surface ocean, right, to down, deep down below. So that means in this case, the pressure would increase, so the volume would decrease. So it makes sense. The volume come out to be less than what its original volume is. Okay. All right, so the next relationship we are going to take a look at is temperature volume relationship of Charles' law. So in this case, I also have the lecture demo as well of the liquid nitrogen and a balloon. All right, in this lecture video, we are going to demonstrate the relationship between temperature and volume of gas. So what I have in this beaker here is liquid nitrogen. Okay, so the boiling point of liquid nitrogen is negative 320 degrees Fahrenheit, which means that if you think about when something boils, like for example, water, you probably think that it's gonna be hot, right? In this case, it's not. Okay, so boiling of liquid nitrogen is actually very cold. Okay, so this is very cold right here. The reason why I say it's boiling, well, because it's just changing the state from liquid, right, to gas. Is boiling, as you see here. Okay, so this temperature is again negative 320. So what I'm gonna do is that I'm going to, so this balloon right here contain a certain amount of gas. Okay, so we're gonna take a look at what happened as the temperature decreased, what happened to the volume of the balloon. Okay, so we are going to dip this in. Okay, so let's take a look at this. All right, as you see, as the temperature decreased, right, the volume of the balloon or the volume of the gas inside the balloon is actually decreased. Okay, so it's directly proportional to each other. Okay. All right, what happened then if the temperature actually increased? What happened to the volume? Well, it's gonna be the opposite effect, right? So let's take a look at that. Okay, so I'm gonna take it out from this. Okay, so now as the temperature increase again, the balloon is going to expand, right? The volume of the balloon will expand to the volume at a certain, like at room temperature. Okay, so back to normal volume again. Okay, so in this lecture video again, it's demonstrate the relationship between temperature and volume. As temperature decreased, the volume also decreased. Okay. All right, from the lecture demo, you already observed that as the temperature decreased, right, the temperature of the liquid nitrogen is negative 320 Fahrenheit. So it's really, really, really cold. As the temperature decreased, you observe that the balloon shrink, right? So the volume decreased. Vice versa, as you take the balloon out of the liquid nitrogen, as the temperature getting warmer and warmer, you will see that the volume of the balloon get to expand as well, right? So that means in this case, the temperature and the volume of a gas would be directly proportional to each other. Okay, so what would happen to amount of gas again? So in this case, still stays the same, right? I did not take anything out of it, right? So the gas should stay the same. And we did not change atmospheric pressure, so the atmospheric pressure still stay the same. Okay, so the pressure of the atmosphere outside the balloon stay the same. Okay, so in this case, so in this case, you can tell that the relationship between temperature and volume would be directly proportional to each other. Okay, so real life example of this would be the hot air balloon, right? So as the temperature rise, the volume of the balloon expand, causing the balloon to be able to like float. Okay, so same thing as well for if you want to fix the dent ping pong ball, right? So you can actually just put it in a hot water. It's going to expand that ball, that ping pong ball will expand, right? So to fix that dent. Okay, so to represent this in a graphical representation, you are going to get, if you plot between volume and temperature, okay, if you plot between volume and temperature, you are going to get the straight line because this relationship is directly proportional to each other. Okay, so note that the unit of the temperature that is plotting is actually in Kelvin. Okay, so in this case, the Kelvin is the absolute temperature scale. Okay, so we need to plot it in Kelvin. So why is it called absolute zero? Well, because if you think about this at 0 Kelvin, right, the volume of a gas also equal to 0 as well. So that's why we call this an absolute zero. Okay. The reason for that is because at 0 Kelvin, ideally, the gas molecule will have no kinetic energy left. It would not be able to move. Therefore, it's not going to exert any pressure on the wall of container. Therefore, the volume, you know, it's going to be equal to 0 in this case. All right, so if we express this in mathematical equation, you are going to get volume and temperature to be directly proportional to each other through these R constant. And as we mentioned, right, the constant that we are looking at would be what? It would be pressure and number of mole of gas, right? Okay, so if you rearrange this so that the constant is by itself, you will see that if you have two set of condition, okay, if you have two set of condition, you are going to get V1 over T1 equal to V2 over T2. Okay, so this is going to be used in the two set of condition type problem. Okay, so let's take a look at this. So again, this is when atmospheric pressure and number of mole constant. Okay, so let's take a look at example. Okay, so a gas in a cylinder with a movable piston has an initial volume of 88.2 milliliter. If the gas is heated from 35 degrees Celsius to 155 degrees Celsius, what is its final volume in milliliter? Okay, so assume constant pressure. Okay, all right, so we have V1 is given T1, is given T2. Again, it's giving you two set of condition, right? Two set of temperature, giving you two set of volume as well. So in this case, we are going to look at that the temperature increase by going from 35 to 155. We should expect that the volume should increase as well. So your final answer should come out to be higher than 88.2. Okay, so now if you remember, the temperature have to be in absolute temperature. So therefore, you need to convert those degrees Celsius into Kelvin first by adding to 273. Okay, so recall that. Okay, so Kelvin to Celsius. Okay, so you're going to add degrees Celsius by 273.15. Okay. All right, so if you do that, you are going to get this as the temperature in Kelvin, and then you just solve for V2. If you solve for V2, you are going to get 123 unit would be in milliliter. Okay, so again, we expect that the volume should increase and is increased. Okay. All right, the next one that we are going to take a look at is the mole and volume relationship. I also have the lecture demo for you to watch as well. Okay, so in the lecture demo that you are going to watch is going to be the reaction between Alka-Seltzer reaction. Okay, so Alka-Seltzer contain the sodium bicarbonate, okay, and the citric acid. Okay, so these two, when they are in a solid form, they're not going to react. They are going to react only when they dissolve in water, which is in aqueous form. So as these two are dissolved in water, they are going to become aqueous, and that's when they are going to react. And upon that reaction, they are going to form carbonic acid that eventually is going to decompose into water and carbon dioxide gas. So that's what you are going to observe, right? So as sodium bicarb react with citric acid, you are going to see that eventually it's going to generate gas, and that gas is carbon dioxide. Okay, so we are going to capture carbon dioxide in the balloon. Okay, so let's take a look at that. All right, in this demo, you are going to see the reaction between Alka-Seltzer and in water. Okay, so in Alka-Seltzer is contains sodium bicarbonate and citric acid. These two in solid form, they are not going to react, but they are going to react in the aqueous form. Okay, so that means if we dissolve Alka-Seltzer in water, it's going to pretty much generate carbon dioxide gas. Okay, so what I'm gonna do is that in this balloon right here, it's already contain crushed Alka-Seltzer. I'm going to add Alka-Seltzer into this water right here, and you are going to see the formation of carbon dioxide. Okay, so we are going to trap that carbon dioxide gas that is producing using this balloon. Okay, so what I'm gonna do is I'm going to start doing that. Okay, so this demo would demonstrate the relationship between the number of mole of gas that is produced with the what do you call it, the relationship between its volume. Okay, so as you see here, right, so the volume as the number of mole of gas increase, you will see that the volume of the gas is also increased as well, right? So which makes sense. Okay, so as the gas produce more and more, the volume is going to increase more and more. Okay. Okay, so again, this is happen at a constant temperature and atmospheric pressure. I'm not changing any temperature or pressure at all. The only thing that changed is the number of mole of gas that is generated and the volume of the container. Okay, so that means the relationship that you see here is that as the number of mole of gas increase, the volume of gas also increase as well. So as you see in the lecture demo, before any reaction, there is no carbon dioxide. Therefore, the volume of the balloon will just, it doesn't have anything, right? So as the number of mole of carbon dioxide increase, or as the reaction progress, there are more mole of CO2 generate more and more. You will see that the balloon start to expand more and more and more, right? So that means in this case, you can see that as the mole of CO2 increase, the volume also increase as well. So in this case, I did not change any temperature, so it stayed the same, and I did not change atmospheric pressure as well, so it stayed the same. So therefore, in this case, under constant pressure and temperature, we can say that the number of mole of gas and the volume are directly proportional to each other. Okay, so that's the relationship between these two. Okay, and the real life example of this is would be bread rising, right? So as you add yeast into bread, right, and wait until it rises, is the process of yeast what do you call, like, ingesting the sugar within the bread is going to cause the carbon dioxide to form, and that carbon dioxide gas as it's formed is going to cause the bread to rise, right? So the next one is if the tire deflated, right? So if you pump the gas in there, pump the air in there, right? So it's going to cause the volume to expand. Okay, so that's the relationship between mole and volume. So this Avogadro's law right here can be expressed by volume equal to constant time number of mole. Okay, so again, the constant that we are talking about here is going to be pressure and temperature. Okay, so as those stay constant. So if you rearrange this equation so that the constant is by itself, you are going to get volume over mole equal to the constant. And if you have two set of conditions as the atmospheric pressure and temperature constant, this is going to be the set of equation that you can use, okay, to figure out either volume or number of mole of gas. Okay. All right, so let's take a look at example here. So in this case, we have a certain number of mole inside the balloon, and it has a certain volume. Okay, so it's asking for the new volume when 3.57 mole of helium is added to the same balloon. Okay, so in this case, we have the two set of condition. Okay, so we have number of mole and two set of volume. So in this case, you will see that as number of mole increase, you should because the mole is added to it, right? You should expect the volume to increase as well. So therefore, our new volume should come greater than 2.85. Okay. So now I'm going to plug off this in. If you do this, you are going to get 17.5 liter. Okay. This answer is incorrect. Wait. Why? Why is it incorrect? Remember, the number of mole given 3.5 is the number of mole added. Okay, so this is not N2. So when you read the problem, you need to be careful whether is the final amount of mole, or it's just the mole that is added, or is the mole is escaped, right? You have to read that carefully. In this case, it's telling you that it's added to, right? So in this case, the actual number of mole of the final volume should come from the original mole add by 3.57, right? Because that's the amount that you add to the original number of mole. Okay. If you do that, you are going to get V2 equal to 20.4 liters. So this is the correct answer. So again, whenever that you are looking at or dealing with the problem of involving Avogadro's law, you need to make sure that you read the problem carefully. Whether is the amount that added, or is the amount of escape, or is the total amount already. Okay, so you need to be careful with that. Okay, so all right, so let's take a look at number 2 here. So this one, I would like you to actually do it yourself. So resume the video again when you finish. Okay, let's check your answer together. Okay, so in this case, we have two set of conditions. So again, I can flip any of this, right? So if you are looking at volume, you can have volume on top and mole on the bottom, as long as they are the same set. Okay, you can do that as well, depend on what you are looking at. So this is when you are wanting to obtain volume. This is when you want to obtain number of mole. Okay, so in this case, I'm going to use N1 over V1 equal to N2 over V2. Okay, so all I need to do is I'm just going to go ahead, plug those in. Okay, so I got N2 equal to 6.97. Is this my final answer? The answer is no, because it's asking you for how many mole of gas have escaped, right? As is deflated too. So in this case, this is the amount of mole that is left, right? Therefore, in this case, you will need to obtain how many mole of gas escaped by subtract from the original number of mole. Okay, so you're going to get the mole of 5.58. Okay, so that would be your final answer. All right, the next relationship that we are going to take a look at is temperature and pressure, or Amundsen's law. Okay, so in this case, we are going to watch the news, and then we are going to take a look at the relationship later. All right, from the news that we watch, we can see that as the temperature increase, you will see that the pressure also increase as well, right? So in this case, the amount of gas inside, sorry, it's not the balloon here, sorry, inside the can. So let's change that real quick. Okay, so this would be can, okay, would be the same, okay, so it stay the same. Okay, and we did not change the volume of the aerosol can at all, so the volume stay the same as well. So in this case, we can say that as the number of gas and the volume stay the same, as the temperature increase, the pressure will increase. Okay, so that's the relationship that we get out of here. Okay, so this is why every aerosol can, there would be the caution that you need to read, right? Like, do not expose it to a certain temperature, right? Because the reason for that is because as temperature increase, the pressure increase is going to cause that aerosol cans to burst out. Okay, same thing for this thing is used for the pressure cook as well, right? So as temperature increase, the you have a fixed volume, you are going to end up with the as the temperature increase, if you have a fixed volume, you are going to end up with the high pressure as well. Okay, so if you are doing synthesis later on, if you are taking organic chemistry class, you will see that whenever that you are set up the experiment, your instructor will say that make sure that your system is not a closed system. And the reason for that is because if you have a closed system and you have a high temperature, you are going to end up with a high pressure as well, and that is going to cause all the glassware to break. Okay, so the relationship between temperature and pressure, as we already see, is going to be direct relationship. Okay, so as you plot between pressure and temperature, you are going to see a straight line of direct proportional relationship. Okay, so again, the temperature have to be in absolute temperature. All right, so if we again express this in mathematical equation, you are going to get pressure equal to RT. And again, R is the constant, which is going to express the volume and number of mole of gas that have to stay constant. Okay, so if you rearrange that so that the constant is on the same, on just by itself, one side, you can get the set of two condition, which is the P1 over T1 equal to P2 over T2. Okay, so let's use this together. Okay, so if you use this in example like this, right? So 700, we are looking at two different pressure and at different temperatures. So in this case, asking you what should be the temperature that is going to have the pressure of 760 millimeter mercury. Okay, so in this case, we know that those given are P1, T1, and we are looking at T2 and given P2. Okay, so if you looking at this as temperature increase, but we should expect the temperature to increase as well. So that means your final answer should come out to be higher than 25 degrees Celsius. Okay, if you plug off this in, make sure that you convert those temperature into absolute temperature as well. If you actually calculate this correctly, you are going to get T2 equal to 324 Kelvin. Okay, so as we expect, right, temperature increase, pressure also increase. Okay, so this is the summary of this chapter section. Okay, so we are looking at different relationships between pressure, volume, temperature, volume, mole of gas, and pressure and temperature. Okay, so of these, you should be able to practice more by starting the homework chapter 9.2. If you have any question, again, please do not hesitate to visit me during office hour.